Hello, everybody. Thank you so much for joining us today. We've got an exciting session, Decarbonizing the Gas Grid, Opportunities and Challenges for Water Heating. My name's Aaron Weiner, and I'm with the Northwest Energy Efficiency Alliance, and I'll be moderating today's session. So before we kick things off, a couple housekeeping items to go over that you probably have heard, but I'm going to review them just in case. Just as a reminder, you can customize your screen, so feel free to move things around and test it out. If you're not seeing what you'd like where you want it, just move it. The presentations will be available as PDFs from the resource list, which I believe is on your right-hand side. You're going to be in listen-only mode, but please feel free to submit questions through the Q&A box at any time, and we will try to hold the questions until all three presentations are complete. These presentations will be available for on-demand viewing in a couple days on the Engagement Hub. And then right after our three presentations, we're going to take some questions, but then we also have a Zoom room that's set up so that we can have a little bit of extended dialogue. And there will either be a Zoom widget on your screen or there is a daily Zoom link available on the Engagement Hub. Also, I want to make sure that y'all participate by letting us know your feedback and fill out the forum survey after the last webcast that you attend. And that really helps ACEEE in planning for future forums. As always, we want to definitely thank our sponsors and partners for the support of Hot Water Forum. And with that, I get to introduce our panel of speakers. So we're going to start off today with Paul Glanville, who is a R&D manager at the Gas Technology Institute. Then we're going to hear from Yan Zhao, who's a research scientist at UC Irvine's Combustion Laboratory. And then Kevin Wu with Socal Gas. He is an appliance test lab lead. So we're going to start things off with Paul Glanville, as I mentioned, R&D manager at GTI. He's been there for 12 years. So I think he started when he was, probably 15, 20 years old. He's in their building energy efficiency group, and he leads a team of engineers and scientists focused on end-use equipment, research and development. His background is in mechanical engineering with degrees from UC Davis and University of Washington. And Paul is going to talk about how blended hydrogen can impact, blended hydrogen impacts on water heating equipment. So with that only slightly bungled introduction, I will hand it to you, Paul.
Thank you, Aaron. Really thrilled to kick off this series of presentations here with my fellow distinguished speakers. So the first, what I'd like to do first here is just give an overview of blended hydrogen impacts on water heating equipment. For assuming that those of you listening are not all as enmeshed in this topic as I and my fellow speakers are, I will be going over some basics of hydrogen combustion as a fuel, because it is a very different fuel from natural gas, which is the major constituent of natural gas as methane. So what I'll do is I'll talk about some pathways, sort of the why are we talking about hydrogen, some very basic topics of hydrogen as a fuel. I'll talk about some impacts on water heating equipment based on some testing done at GTI, and then some near-term opportunities and challenges. We'll be using a lot of combustion-related terms today. One example shown here, non-premixed or diffusion flames all the way through premixed flames as a way of describing how much air, if any, is mixed with the fuel prior to combustion. And so what are we actually here to talk about? First, you should see a video of a water heater burner operating with a 30% hydrogen blend with methane. And this is really what we're talking about. This is the hot topic for this particular session here. We want to see what are the impacts when we change the fuel by adding this low or no carbon addition to natural gas. The first version you saw was a standard burner operating in most gas water heaters. This is an ultra low NOx version operating in water heaters in California and more recently in the Salt Lake City area of Utah, so ultra low emissions version of the same thing. These are the workhorses of water heating, but let's first talk about decarbonization. So for the more than half of homes and businesses that use fuels for water heating today, we need to acknowledge that this is a large set of the building stock. Over 80% of homes, for example, were built before the year 2000. The average lifespan of the home is in the U.S. is estimated of about 130 years. So when we're looking out to 2030 and 2050, a lot of the buildings that we need to decarbonize exist today. And for those that are served by fuel-fired technologies today, where they may be mostly existing buildings in cold climates, where they have thermally intensive loads, or increasingly where decarbonized fuels are available on a regional basis, the technology needs are sort of more of what we talk about through this forum and others: gas energy efficiency, thermally driven heat pumps, micro CHP, and fuel cells. We'll focus today on the fourth item here, hydrogen-fueled equipment. Of course, there is a second and a different branch of where decarbonization will play out for these buildings, and this will be primarily served by electric technologies or electricity as a delivered energy source. This may apply mostly to new construction or mild and hot climates, low energy net zero designs as applied, areas where renewable electricity is plentiful and cost effective. The technology needs will differ for these, where balancing services on the grid side will be more important. DERs, a lot of the other topics that are addressed throughout timely forums like this will apply there as well. So again, we're going to focus on the first pathway here and hydrogen as a fuel. So let's talk about why. Decarbonized fuels can be coupled with energy efficiency to really drive greenhouse gas emissions reductions. I think most folks are aware that hydrogen as a fuel emits no CO2 directly, and it can be blended with natural gas or biomethane for standard products, and there can even be specially designed equipment to use 100% hydrogen for heating applications or other applications as well. Hydrogen doesn't really exist on its own, but it can be viewed as a way of storing a lot of energy for a long period of time, and that energy can be renewable. So that's really why it's having a bit of a moment right now. Now let's just kind of illustrate this in sort of a simple way. For most of the water heaters out there using delivered fuels today, these tend to be low efficiency storage type. We can offer a blended decarbonized fuel to those products to drive a roughly proportional reduction in greenhouse gases. Of course, as we know through ACEEE and their leadership, that energy efficiency is often the best place to start when you want to reduce greenhouse gases. And with heat pump technology for fuel-fired products, we've shown in previous studies that we can reduce a significant amount of greenhouse gases. Now, what we're talking about today, where we're driving, is combining the two. So going with high efficiency and decarbonizing the fuel, either partially for this talk today, or in the future with pure decarbonized fuels. So where does this fit in context? GTI recently joined EPRI in an effort called the Low Carbon Resource Initiative. And this is really looking at an economy-wide decarbonization strategies through 2030 and 2050. And while this is somewhat of a complicated diagram, this represents in a simple form, believe it or not, how these kind of decarbonized energy carriers, hydrogen, ammonia, carbon capture, these things that are scaling up right now can play a role in how we decarbonize, how we use energy in the future. For us, in water heating, we're looking at buildings on the upper right-hand corner where it's possible in the future where delivered or pure or blended hydrogen may be a part of our energy mix, and this is what we're going to talk about today. So let's talk a little bit about history here. Blending hydrogen with delivered fuels is not new. In fact, before natural gas, there was town gas, and in a way, natural gas as a term is intended to distinguish from that. I used to live in Seattle, and there's a great park there called Gasworks Park, which is a former coal gasification facility that delivered town gas to Seattle in its earlier heydays. That gas is about 50% hydrogen in most cases with balanced traditional hydrocarbons. And that, whether it's from gasified coal or others, it tended to be used for lighting and then later for indoor use. Now, of course, after World War II and the expansion of natural gas as a delivered fuel, a lot of this was phased out, and that particular facility was turned into a pretty cool park there off of Lake Union. But there are places, such as on Hawaii, on their main island, where there are delivered fuels today that do contain some hydrogen. And it's a sizable amount of customers there. Of course, this legacy exists in terms of how we design and certify equipment, as these manufactured gases, as they're called, are part of current studies and standards, in addition to propane and natural gas, how products are certified today. Of course, in Europe, where hydrogen is looked at a little bit more seriously as a delivered fuel for decarbonization, appliances today are certified with a hydrogen blend of up to 20% to look at changes in gas quality, which tend to be a wider variation than we see in North America. Now, there's a lot of activity in this space right now, where hydrogen is being looked at as demonstrations to generate, store, and use hydrogen at multiple scales. A lot of them are in Europe or Asia, as shown here, but increasingly they're in North America as well. And we'll hear about Kevin's work in Southern California, really interesting updates there in North America. Now let's talk about hydrogen too. It doesn't exist in the same way as electricity. It's generated from something. So in terms of carbon content, we have to be mindful of this. Brown hydrogen and gray hydrogen, these colors that are often used, represent fossil sources of hydrogen today. And for gray hydrogen, steam methane reforming of natural gas, this is the vast majority of hydrogen that's used today and generated. However, in the future and the near term, we talk about blue hydrogen and green hydrogen, whether it's a gray hydrogen with carbon capture or if it's generated from renewable resources as a form of storing excess renewable electricity or utilizing a renewable stream. There are a lot of studies looking at how these colors of hydrogen will shift over time, but I think really the goal is to shift towards green hydrogen as far as the color spectrum is concerned. Now, when we add hydrogen to natural gas, it really can be first viewed as a gas quality issue because natural gas does vary in gas quality, how appliances handle these shifts in the constituents of natural gas today. Building on a lot of efforts in Europe, where GTI and some of our colleagues are involved, there are 3 general tiers of blending when it comes to how it impacts equipment, and they're shown here by volume. So, for instance, 10% by volume in most cases. No or minor adjustments are necessary to existing equipment. Medium blending, 10 to 30%. Again, these are very broad numbers. Maybe some small adjustments are possible with combustion hardware or controls. And then high blending, roughly speaking, 30% or above. At this point, you might as well be designing a specially designed piece of equipment to handle pure hydrogen. And these are sort of general rules of thumb. And why is this? Hydrogen is a very different fuel. This chart shows some of the properties that we'll explore throughout the session here, where it's that while it does have no carbon dioxide emissions as it's used, that response is nonlinear due to the fact that it is a much lower volume as compared to methane, and also has a reduced heating value as well. It has a hotter and faster flame, it's more readily lit, and it can also impact NOx emissions, flame stability as a result of those 2 properties. And finally, I think as sometimes discussed, hydrogen has long-term impacts on equipment as well due to the fact that it's very small, it can leak, and it also can impact materials as it does that. It also has a reduced requirement of combustion air as well as you blend it with methane, and we'll see how that offers some benefits in some testing. Now, for the vast majority of burners that are out there today, we can put them into 3 broad groups. And this really has to do with how air is mixed with fuel prior to ignition. If there's no air mixed, if fuel and air meet at the point of combustion at the flame, we call it a diffusion flame. These are not as common in a lot of the applications we're talking about here. Pilot light is one example, but in some cases, some fireplaces are operated in this way as well. Partially premixed, where some air but not sufficient. Lambda as a marker, in that case, is between 0 and 1. This is the vast majority of burners that are out there today that are operating in our homes and businesses. And premix, which is often used for higher efficiency equipment, compact equipment like tankless water heaters and ultra-low NOx versions, as it is a good way of reducing NOx emissions. This is where fuel and air are carefully combined prior to ignition and often can be controlled independently of one another, which is not the case for partially premixed. So these distinctions we will refer to throughout this session. Now, for water heaters, one of the first things that we notice is that because of its reduced volumetric density, adding hydrogen will derate or reduce the heating rate of the water heater, meaning that less BTUs will be delivered from the flame to the water heater itself. And that's a universal property. For partially premixed burners, which represent the vast majority of those applied in water heating, both commercial and residential type, other things that we'll notice is that the primary aeration, the amount of air that's mixed with fuel prior to ignition, will shift towards stoichiometric, meaning it will increase. It will go towards 1 in most cases. And this is important because we're talking about a change in flame speed. A lot of concern with adding hydrogen means that we may have flashback, which is where the flame actually kind of sucks back towards where the fuel and air are coming from, and the flame will often go out. The system will need to be addressed as a result. The opposite impact, where the fuel and air flow rate is faster than the flame speed to the point that the flame blows off, is not as much of a concern in this case here. Now, also the flame may be hotter, and it also may have stability issues as well as noted. Where things get complicated is that the burner design, the combustion chamber design, how the flue or the venting is deployed, the back pressure, all of these things will have impact. So these are not necessarily predictive traits. We'll see that with some results in just a second. However, there are two indices that are important when just talking about the amount of hydrogen we're adding. It does impact the Wobbe index, which is a frequent term used in gas interchangeability. This represents the for processes that have the same Wobbe index, the heating rate delivered to the appliance will be the same for an orifice where the fuel is coming out with a fixed pressure. So this is really a way, will it have the same heating rate, roughly speaking. And for hydrogen, the Wobbe index is much more stable than some of the other properties we're talking about. Another property which is also applicable to partially premixed flames is the combustion air requirement index. And you can see it's defined by the air-to-fuel ratio based on the fuel properties. This gives us a sense of how the primary aeration, or lambda, will be impacted for partially premixed equipment. Now, laminar flame speed and adiabatic flame temperature can also be predicted based on the fuel mix, but these are of more theoretical value, and we need to do some testing or have some other experimental experience to understand what the impact is on the burner itself. Premixed equipment will have different responses here, but often the controls are fine enough that they can be compensated for. So let's look at an example here. If we take a pancake burner, a very standard burner in water heating, and we have a standard representation of natural gas here, a Wobbe index of 1373, a specific gravity, a way of showing the volumetric density as shown. The firing rate is shown. The primary aeration is shown as 60%. That means 60% of the air for full combustion is mixed with air prior to the point of ignition. The air-to-fuel ratio and the combustion air requirement index are also defined. If we take that same burner and we add 30% hydrogen by volume, you can see how things are impacted. The Wobbe index reduces by a slight amount, meaning that our heating rate will reduce slightly as well, but a much larger reduction in the volumetric specific gravity of this particular fuel. Firing rate will decline as a result, meaning the heating rate to the appliance will also result. We'll show later on the test results suggest that the efficiency really doesn't change as much, but the capacity will, so the unit will run longer, but not necessarily less efficiently. Primary aeration goes up, and air-to-fuel ratio and combustion air requirement index are also impacted. Now we can chart some of these properties here. This shows the laminar flame speed for different blends of hydrogen based on a GTI model. We start at the blue point here and move to the green point here. And why is this important? You can see our flame speed is increasing. We're also going towards lambda is equal to 1, or the equivalence ratio, the inverse, is equal to 1 as well. This can mean that we may look for stability issues with this particular case here. On the premix side, where we're on the other side of the dome, depending on how air is controlled, we can either shift left or go straight up if we have a constant lambda or a device that tries to maintain a fuel-air ratio through advanced controls. So I think the overall point is that it's complicated. We can learn some things about what happens when we add hydrogen, but we don't know everything. But like most instances, the heating rate decreases, air-to-fuel ratio, air and flame speed will increase, but we can't say much about flame temperature or NOx or stability. So these show you some photos of most of the appliances out there. Let's talk very briefly about some of the studies out there today. The industry consensus is that most appliances can handle 5 to 15% hydrogen. This is largely based on studies looking at what's been happening with Europe. There's been a lot of activity in this space. You'll hear about some of them today. The level of hydrogen blending varies in these studies. What the balanced fuel is in GTI study, and others it's balanced methane, and others it's balanced natural gas. And then what equipment are selected and what burners are operated also vary, and of course how they are operated. So there are some knowledge gaps that remain. What is the impact on larger populations of equipment? What happens when we have a different balanced fuel, a wider range of operating conditions? Or of course, what are the long-term impacts on the equipment life as well? These are all open questions at this point. So let's get quickly into some results before I wrap up here. GTI is engaged in some testing of water heaters and other appliances with up to 30% hydrogen blends. You saw a video up front on some early results here. We're looking not only at the ignition and flame stability and location and behavior of the flame, but also emissions results. We're looking at the appliance operation, the impact on efficiency, and other more customer-facing impacts like noise, excess condensation. And this is an effort to align with some of the other studies that are underway in Europe. First set of tests we did was open air. You can see some results here looking at standard and ultra low NOx type burners with 100% methane or 30% blends. What we see here, generally speaking, is that the wall temperatures of the burners do increase a little bit, up to 20% hydrogen, small reductions in emissions, but no noticeable changes in ignition and stability with these open air tests. Now, when we're firing into the appliance, we perform a number of standard tests and also slug tests, where we are rapidly changing the fuel mix. And while this is somewhat of an academic exercise, it's also intended to represent that there may be slugs of different hydrogen concentrations moving through a building's network as a lot of gas equipment cycle, in some cases on a daily basis or even seasonally. So we want to capture that, as you see here, shifting from 5% to 30% hydrogen and back again as the unit is continuing to operate here. A lot of our testing is also from cold and hot starts. We're trying to cover the wide range of operating conditions here. This just shows you a snippet of some of our results on the emissions side. It's really, for one thing, if we can reduce greenhouse gas emissions, that's great, but if we increase NOx emissions, that may be a problem. So you see here that in both cases, because we're adding a fuel that requires less combustion air while we're keeping combustion air roughly constant, that this tends to cool off the flame by dilution, and you can see the NOx emissions in green on both charts, either roughly flat or declining in both cases here. I mentioned before that efficiency is roughly flat, while there is a measurable D rate for these products. So let's just cover what's next here. GTO will be continuing to perform short and long-term tests on these kinds of equipment and other appliances as well, moving from furnaces to fireplaces, cooking products and boilers. We'll be sharing these results more widely outside of presentations like this. We're also looking at parallel efforts to introduce small-scale hydrogen sensors into equipment and small-scale distribution, and also importing and tech transfer with 100% hydrogen-tolerant products under development abroad. And there are a number of blending efforts underway, studies underway, where in the field we can also apply some of these techniques. And then finally, we talk about hydrogen, but there's also renewable natural gas or biomethane. We do have some studies underway looking at the impact on trace contaminants in that kind of replacement natural gas, and also on the back end, looking at what we can do in larger buildings in directly capturing the carbon dioxide. So looks like I went over a little bit here, but thank you for your interest.
No worries, Paul, and thank you. Way to end up with that teaser of showing off that big black box. So thanks again, Paul. Our next speaker is Yan Zhao, and Yan is a research scientist at the UC Irvine Combustion Laboratory. You'll see in just a minute, he is literally there. Yan has experience working on both domestic combustion systems as well as gas turbine combustion for power generation. And right now, he's working on renewable hydrogen adoption in residential appliances. So Yan's going to kind of build on what, or maybe zoom in on some of what Paul was talking about and talk very specifically about hydrogen-fueled impacts on residential equipment, some of the simulation and testing results that they have seen there. So with that, Yan, I will turn it over to you.
Yep. So thank you, Aaron, for the very nice introduction. So hello, everyone. My name is Yan Zhao. I'm from UC Irvine Combustion Lab. So I'm going to share some of our experimental results today on hydrogen-fueled impacts on residential equipment. So we are located in California. So California has a very ambitious carbon reduction goal. So by 2030, it's trying to reduce the carbon emissions 40% below 1990 level, and 2050 is going to be 80%. And by the year of 2045, California is trying to achieve 100% renewable electricity. So one way to help achieve these goals is to blend some renewable gases into the pipeline natural gas. And the challenge is what would be the influence of the renewable gas on these appliances we already have. And here shows the California residential appliances status. So on the left side, you can see around 49, like 50% of the residential natural gas is consumed by the water heating section, and 37% by space heating, and the rest would be cooking and dryers and other applications. For electricity use, it's kind of different. The water heating and space heating only takes around 5% of the electricity use, and most of the electricity is used in lighting, fridges, and TV or computers. So down there on this plot, you can see the different appliances types. So the dark bars stand for the gas appliances, and the light color bars stand for electric appliances. So you can see for water heating appliances, around more than 90% of the appliances in California are still gas appliances. So it's very promising if we want to replace the natural gas with some renewable gases, especially hydrogen, because hydrogen is carbon-free. And so when we want to replace pipeline natural gas with renewable hydrogen, we want to understand what's the difference between these two fuel classes. So you can see the comparison chart here. And methane is one of the major contents in natural gas. So you can see hydrogen has a much lower density compared to methane. And also the flame speed of hydrogen is 5 times that of methane. And also the flammability range of hydrogen is much wider than methane. So one of the main properties we care about in combustion devices is the heating load. So you can see the equations here. The heating load is proportional to the Volbe index. So that means when we don't change the pressure drop from the pipeline to the combustion device or the combustion device parameters, the heating load of the combustion device is going to be proportional to this Volbe index. And so even if hydrogen has a much lower heating value on a volume base compared to methane, the Volbe index of these two fuel classes are quite similar. You can see here is 52 megajoule per cubic meter, and hydrogen is around 48.5. So that means when we're trying to replace hydrogen, when we try to replace natural gas with hydrogen, the heating load will not change too much. So on the right side, you can see the chart here, and the curves are the variation of the heating value, the red curve, and also the Volbe index is the green curve. So from pure natural gas to 100% hydrogen. And the dashed lines are the gas quality regulations by Socal Gas, because here Socal Gas company provides natural gas for us. And the heating value lower limit is 990 BTU per cubic feet. Actually, this is kind of an old regulation. I think Socal Gas updated the regulation in 2019. I think Kevin is going to cover that later. And based on this regulation, we can inject around 3% hydrogen into the pipeline natural gas. And the Volbe index, due to the similarity of the Volbe index of these two fuel classes, we can inject around 14% hydrogen. But in our study, we're not limiting ourselves based on these regulations. We just want to see how much hydrogen we can inject into different appliances. And also hydrogen doesn't, the Volbe index doesn't consider other combustion properties, including flame speed, flammability, or ignition performances. So we want to see what's the influence of hydrogen on all these kind of combustion performances. And the emissions would be one of the major concerns for current water heating applications. You can see here are some selected NOx emission regulations and CO emission regulations in America now, because we are located at Southern California, and we have the South Coast Air Quality Management District here, which has almost the most strict regulation in North America. So currently, the most strict regulation on NOx emission is 10 nanograms per joule, or 15 ppm, based on 3% oxygen correction. And in the year of 2015, the state of Utah also adopted this regulation. So more and more states are trying to adopt this low NOx water heater regulation. So if you want to buy a water heater online, for example, from the Home Depot, you can check. There are like notes here saying that, oh, CA or California or Utah residents, you need to check on the labels. And there are usually two types of labels. One is saying that maybe this water heater doesn't meet the ultra low NOx regulation. Some water heaters saying that, oh, we meet the low NOx standard of California. So AQMD are certifying low NOx water heaters. If you go to their website, you can check what water heaters are considered as low NOx or ultra low NOx water heaters. So usually there are two types of residential water heaters. One is the storage water heater, one is the tankless water heater. So we tested both types. So today I'm mainly going to talk about the tankless water heater here. So you can see here we have the fuel mixing panel. We try to mix different fuels together and then supply the fuel mixtures into the water heater. You can see there are two stages of heat exchangers, the primary heat exchanger in the tankless water heater and the secondary heat exchanger, which is trying to condense the water from the exhaust, so trying to take more heat from the combustion. And we have different HORIBA emission analyzers trying to measure different emission species, including NO, NO2, N2O, ammonia, CO, unburned hydrocarbons, etc. So here is the plot of the NOx and CO emissions of the tankless water heater we tested. So the red curves are NOx emissions and the blue ones are CO emissions. And we tested two different flow rates. One is 2 gallons per minute water flow rate, and the other one is 4 gallons per minute. So from 0% hydrogen addition, which is pure natural gas, to 20% hydrogen addition, we can see a slight decrease of the NOx emission, and here's the 4 gallons per minute. But the CO emissions fluctuates a little bit. And there are different types of correction methods. So the first plot is the ppm level based on 3% oxygen correction. And we also have the CO2 correction. And here we have calorific correction, how many nanograms per joule emissions. So generally speaking, hydrogen addition into this tankless water heater will decrease the NOx slightly, but doesn't change the CO or NOx or unburned hydrocarbon emissions. And the second plot shows the air-free correction, which shows a relatively flat curve. You can see the decreasing trend of the NOx is not too obvious. This is due to the property of this equation. You can see the CO2 is in the denominator. So when we try to replace the pipeline natural gas with renewable hydrogen, the CO2 in the denominator will decrease. So the total value of the emissions will increase. So that's why we see a relatively flat curve here. And also the water flow rate also influences the emissions of this water heater. So some other observations. For this tankless water heater, we did see a higher water condensing rate from the secondary heat exchanger as we add more hydrogen, because the only products of hydrogen combustion is water. So we did see some more water coming out of the water heater from the condensed heat exchanger. And also we did see a slight efficiency increase when we try to replace pipeline natural gas with hydrogen, but the increase is not very obvious. So that was the tankless water heater. And we also tested different other different appliances, including cooking appliances. You can see the cooktop burner, oven burner here, and also the room furnace for air heating. And we did both experiments and simulation on these appliances, and we submitted a report to California Energy Commission last year. So if you are interested in the report or our experiments results, feel free to reach out to us. We can share the report with you. And so this is the general experiment setup for our burner testing. And we have this mixing panel here to blend the different fuel mixtures, and we have cameras to characterize the flame structure and to measure the burner temperature and other performances. And we have different HORIBA emission analyzers to measure the emission species, and we are also monitoring the combustion noise or temperatures. And we also did the CFD simulation on different burners. So here is an example of the cooktop burner we have. You can see here's the 3D model simulation and also 2D model. So we are trying to divide the combustion region into different sections, and we use different reaction mechanisms trying to predict the flame position and also the emission species. So here is the broader perspective on the carbon reduction benefit of replacing pipeline natural gas with renewable hydrogen. So we have basically 9 different types of appliances in California, and when we try to replace the natural gas with hydrogen, for example, here we can see 5%, 10%, 15, 20% of hydrogen. We are not actually reducing the carbon emissions by the same percentage. For example, when we replace the pipeline natural gas, 20% of that with hydrogen, we are not actually reducing 20% carbon reduction because different burners have different operating mechanisms. So we are reducing less than that. So conservatively speaking, when we, if we want to replace around 10% of the pipeline natural gas with hydrogen, so we can reduce 1.63 million tons of CO2 every year in California. And this is equivalent to around 354,000 gasoline vehicles being removed from the road. And in our lab, we're also doing a big picture analysis on how the hydrogen addition to the pipeline natural gas will influence the air quality in California. So this is the project we are cooperating with South Coast Air Quality Management District. So here is the primary result. When we try to replace the pipeline natural gas, we can reduce some NOx emissions from the combustion devices, which influences the ground ozone level. Again, if you are interested, please contact us so we can share the results with you. So thank you for your attention. And here I will hand it over back to Aaron.
Great. Thank you so much, Yan. That was really great to see not only the findings from your research, but also to see your lab there and some of the equipment that you use to gather that information. Really connects things. And for me, at least, it helps to really understand the whole process. So thank you. Next up, we're going to hear from Kevin Wu. So Kevin leads the appliance test lab at Socal Gas and really focused on appliance and equipment testing for performance, energy efficiency, as well as emissions. Kevin's previous experience has been with distribution pipeline engineering and pipeline integrity management, and he's been with Socal Gas for 14 years. So today he's going to cover opportunities and challenges with decarbonized fuels from the utilities perspective. So Kevin really represents where the rubber hits the road, or in this case, where the gas hits the pipeline. So with that corny joke, I will turn it over to you, Kevin.
Thanks, Aaron. Appreciate the intro. And thanks, Paul and Yan, for teeing me up, mentioning some of the things that are going on in California. So thank you all for allowing me the privilege of speaking to you today. Like Aaron mentioned, I'll be providing a bit of the utility perspective on the opportunities and challenges with hydrogen blending. So just a little bit of info about Socal Gas. We are the largest natural gas distribution utility in the United States, serving approximately 22 million customers through about 6 million meters. Our service territory covers over 20,000 square miles through over 3,000 miles of transmission pipeline and over 100,000 miles of distribution pipeline. So very recently, Socal Gas announced our goal to become the cleanest, safest, and most innovative energy company in America. We believe that every Californian deserves a clean, affordable, and resilient energy future. And hydrogen is one of the key opportunities before us to make these goals a reality. So in the state of California, our Public Utilities Commission has already opened that window of opportunity for the state's natural gas utilities to help create a hydrogen blending and injection policy that will really ground the hydrogen as a clean energy fuel for California's future. Of course, when we talk about blending hydrogen into our pipeline system, it all starts with safety. Our blending policies in development revolve around the safety of the public, our employees, and the pipeline system. In order to develop and inform our policies, we have been embarking on intense research, collaboration, demonstration projects that will ultimately lead to a blending and injection standard on our system. So if you look at the slide here, right now we kind of stand between the first two parts, between the in progress and the near term. been doing quite a bit of research over the last few years. We've already started this process with the California Public Utilities Commission and working towards that hydrogen injection standard. So just to provide some more detail about the ongoing proceeding with the CPUC, this slide shows the different phases of the Biomethane Order Institute ruling, which actually started back in 2009. So if you see on the slide there, back in the early stages of phase 1, that's where we identified a 0.1% hydrogen trigger level. And then more recently in 2019, the CPUC approved our phase 4 to specifically develop the standards for hydrogen injection in the gas networks, where we stand today. So certainly the opportunity of hydrogen in the natural gas infrastructure is not without its challenges. Paul and Jan have spent some time discussing the unique properties of hydrogen and how they impact our appliances. At Socal Gas, we're looking at hydrogen blending through 3 primary focus areas. So that's safety, reliability, and integrity. So this slide shows some of the critical research topics within each focus area, although the reality is some of these research topics overlap into other focus areas. So today we are, of course, focusing on the impact to end-user appliances. And even though on the slide you see it listed under integrity, end-user impacts definitely touches upon safety and reliability as well. Okay, so what have we done, or what are we doing at Socal Gas to investigate end-user impacts from hydrogen blending? Well, we do have multiple research efforts ongoing now and have already been completed. What's relevant to today's discussion is the residential and commercial appliance testing we conducted between 2014 and 2015. For this test, we investigated several different types of appliances that did include a traditional tank-type water heater with an ultra-low NOx burner and a condensing tankless water heater, which I'll be sharing some info on today. To help us better understand the impacts of blending, we tested at 5% hydrogen by volume, 10% and 20%, and compared those results to our typical pipeline gas. These results included performance measurements such as the energy consumption, flame characteristic observations, such as noting any flame lifting, yellow tipping, or flashback, and measurement of the gas constituents to calculate the heating value data for interchangeability impacts. So very similar to the testing that Paul and Jan have been doing in their respective laboratories. So a couple qualifications that I'd like to point out before we move into the information. First, our lab is an experimental test lab, so we're not a certified lab. So the results that we collect are primarily for learning purposes. The second thing is the key folks who worked on this project back in 2014, 2015, they're actually no longer with the company. So I'm more than happy to answer your questions that you might have to the best of my ability, but I may not have the answers to specific experiences related to the actual testing. And the third thing I want to point out was, although the team did collect emissions data during the testing, the methodology they used was not verified, so I won't be sharing those specific results today. Okay, so here's just a quick look at the test setup. Nothing really special here. In fact, very similar to what Jan presented with the UCI testing. We blended pipeline gas with bottled hydrogen into a manifold using mass flow controllers to ensure the uniformity while taking periodic readings of the blended gas with the gas chromatograph. You can see some of the critical measurement points along the system for measuring temperatures, pressures, and flows. The setup was essentially identical across all the appliances that we tested, with one of the key differences being the tank-type water heater, which included a series of temperature probes inside the tank to calculate the average water temperature inside the tank. And just real quick, here's a photo of what that test schematic looked like in the lab. Okay, so starting off with some performance results on the ultra-low NOx water heater. So as expected, the fuel volumetric input rate in the orange line, it might be difficult to see these colors, and I apologize. The volumetric input rate went up with increased hydrogen concentration, while the energy input rate measured in BTUs went down, and you can see that with the blue line. And as Jan described the impacts to the heating value in the Wabi, we see those declines also with increasing hydrogen. A visual that I unfortunately didn't have available to me for these test results was the heating time for the burner to reach cutout temperature, but I can share that the testing showed a moderate increase in heating time from a starting temperature about 7 degrees Fahrenheit to burner cutout as hydrogen concentration increased. The highest differential observed was about 15 minutes at 20% hydrogen. Here's that same data set for the tankless water heater. So there's some more dramatic bumps in the data due to the modulating operation of the tankless water heater, but overall we see the same patterns of the increasing volumetric flow and the decreasing energy input, heating value, and Wabi index with increasing hydrogen concentration. So as mentioned earlier, the team did make some observations on flame characteristics during all of the appliances tested. Here's an example of the tankless water heater at baseline natural gas versus the different blends of hydrogen. What's key here are the observation notes in the right column, which essentially note that at no point during the testing did the team observe any issues with flame stability, yellow tipping, or flashback. And that same observation was made for all 3 modes of testing on the tankless water heater, so that'd be max, mid, and low firing rates, as well as the ultra-low NOx burner testing. So this is something that both Paul and Jan alluded to. A key challenge that we also kind of mentioned in the previous slides is the heating value and the Wabi number of the gas. Specifically, the limits that we have in place in California. So for the Socal Gas service territory, we have our gas rule number 30, which requires the heating value of the gas, pipeline gas, to be between 970 and 1150 BTU per cubic foot, which Jan did mention previously it was at 990, but we just very recently updated that value on the minimum heating value. While the Wabi number must be between 1279 and 1385. So the table shown here is of 2 examples of the impact of hydrogen on different baseline values. So though there is a more significant impact on the high heating value as hydrogen increases, the Wabi, which again is the interchangeability factor, still remains quite close to the lower limit even at 20% hydrogen. Just as a reference, our pipeline gas in Socal Gas service territory, the heating value is typically around 1040 BTU per cubic foot, but could be slightly higher or lower just depending on the source of the imported gas and the dynamics of the pipeline system on a given day. So heating value and Wabi, these are critical parts of our ongoing proceeding with the CPUC to determine how our Rule 30 and now our updated Rule 45 will be impacted and need a change to safely accommodate for higher concentrations of hydrogen. So the appliance testing we previously went through, though very valuable in our understanding of the impacts of hydrogen, is only one challenge of hydrogen blending that we have been and are actively working on to gain a better understanding and level of confidence to ensure the safety, integrity, and reliability of our customers and gas system. To see this great opportunity that hydrogen presents, Socal Gas will continue aggressively pursuing testing, research, demonstration and pilot projects, and forming and developing key partnerships such as GTI and UCI, all while remaining laser focused on our ongoing application with the CPUC. So with that, I would just want to thank my fellow panelists, ACEEE, and all of you in our virtual audience for the opportunity to present today. Here's my email address. Definitely feel free to reach out to me, and I look forward to connecting with you in the near future. Thank you.
Great. Thank you so much, Kevin. Great job on sharing some of, really the opportunities and challenges around what we're talking about. And thank you for sharing SoCal's kind of vision for the future on that. So we have received a number of really great questions throughout the duration of these three presenters, and we do have some time now to address those. And so I'm going to pose the questions in order that they were received. But if you do have questions, please feel free to enter them in the Q&A box using the toolbar at the bottom. And again, I'll just sort of read them out in order that we're receiving them. If we don't hit them all in the time that we have remaining, we can certainly shift and follow up in the Zoom chat. So without further ado, the first question that we got was, how will increased hydrogen impact indoor air quality issues, which is currently a point of gas system criticism by some. So I think any of you all who are able to answer that or point us in the direction, but again, just the questioner was interested on how and if hydrogen would impact indoor air quality issues.
Well, perhaps I could start. As I understand it, a lot of the indoor air quality issues directed at fuel-fired appliances tend to focus on open flames in the conditioned space, like cooking, for example. Whereas water heating, especially if it's got sealed venting, the products of combustion do not communicate with the indoor space. In the case of standard draft-equipped venting on the standard storage type fuel-fired water heating, that should also still be the case, that unless those particular vents are depressurized through sort of action on the envelope side, that those flue products will also safely vent through and go outside. I think maybe a separate question would be, how does adding hydrogen to the fuel impact air quality through outdoor air that's brought indoors? And given their study with South Coast, maybe Jan, you wouldn't mind fielding that one? That's a good question for you.
Yeah, thank you, Paul. Yeah, I totally agree with what Paul just said. Yeah, so as I mentioned earlier, yeah, so for most appliances, especially larger heating load appliances like water heaters or furnaces, the emissions will be vented out of the room. So for indoor air quality, mainly from the open flames like cooktop burners or oven burners. But with proper ventilation, it should not be a problem. But also with hydrogen injection, as I showed, we see a general decreasing trend of the NOx. And also for CO, when we replace more hydrogen, more natural gas with hydrogen. So if anything, when we replace natural gas with hydrogen, we are seeing a decrease of the NOx emissions, so which might be the benefit of replacing the pipeline natural gas with hydrogen. Yeah.
Great, thank you, Ian and Paul. The next question, and I believe this refers to Paul, your presentation based on the time it was asked. At the beginning of the presentation, 50 to 80% carbon reductions were claimed. And the question is, under what percent of hydrogen addition was that at?
Yeah, that's a very good question. That particular slide was intended to be illustrative, and I think it introduces a key nuance when talking about decarbonization from hydrogen addition. I guess the first point I'd say is that also was intended to include some form of renewable methane in the fuel as well, when applied to the standard or the heat pump case. And that fraction was within the range that's typically reported out there, or that utilities have specific targets for. But when it comes to the hydrogen, it's worth emphasizing that in some cases in our world, we refer to emissions on a volumetric basis, ppm of NOx, ppm of carbon monoxide, for example, which are often terms that represent steady state operation. And if you, on a volumetric steady state basis, if you displace a certain amount of the fuel with zero carbon hydrogen, the proportional reduction of CO2 on a volumetric basis will be proportional. Things break down when you start talking about an energy adjusted basis. And for equipment that are controlled, based on their energy input to the device, which is to say they're serving a thermostat or an aquastat, you start to see the dynamics that I and Yan and Kevin all highlighted, that in the sort of normal operation, if you deliver hydrogen to an appliance, you will reduce its heating input to the application, heated water in this case, and that will result in the unit running longer, and a proportion of natural gas or methane or whatever the balance fuel is will be consumed in excess of what's in the blend. So that's why you see, for example, on a pure basis on the chart that I showed, 20% blend of hydrogen results in a 7% reduction on an energy adjusted basis in CO2, about 12-13% for 30% blend, for example. So it's not proportional and it's nonlinear in that respect. So sort of a long-winded answer, and the figures that were shown were illustrative. They were sort of going up to what was shown for a volumetric comparison, but energy adjusted, it would be at the lower end of that same range where hydrogen is concerned.
Great, thanks, Paul. And I think this is sort of a follow-up or related question, but it's the questioner is just asking, how GTI selected 30%. Is that the highest level of mixing before instability, or were there another reason?
For us at this point, we have been coordinating with folks in Europe during this kind of testing, and I mentioned that rough set of tiers of 30% being sort of the start of the high tier. Our testing so far has shown that ultra low NOx and standard water heaters can operate with a 30% blend. So it stands to reason that we could have had a higher value. So it was somewhat arbitrary for our current test plan.
Great, thanks. And then this is somewhat of a follow-up also. How does that 30% blend change the flue gas dew point, condensate forming behavior, and efficiency of condensing heat exchangers?
Well, I could offer a quick answer, and maybe Yan and Kevin want to add to this. I'd say it's complicated. So on the one hand, if you're burning hydrogen, your only product is water vapor, and that will increase the dew point of your combustion products beyond what it is. However, as you add hydrogen, you also decrease the combustion air requirement. So that means there's more dilution. That also influences the dew point. And just based on some testing we've done and seen sort of first principles, for uncontrolled air, combustion air for these kinds of appliances, this results in actually a net decrease in dew point, so you're less likely to condense. Things change if you have a premix device, I think as the questioner was posing, and you are actively controlling the combustion air and in a constant lambda system, you may see an increase in dew point. So I'd say it depends.
Yeah, so I agree. Yeah, and also I just showed the results for the Tankless water heater, and we did see the condensing rate from the secondary water heat exchanger goes up when we replace the natural gas with hydrogen. So when we replace more natural gas with hydrogen, we think we are going to give more pressure on the secondary heat exchanger, because the only product of hydrogen combustion is water. And so for higher percentage of hydrogen blending, so the secondary heat exchanger of the water heater might need to be modified, I think.
Great, thank you. Next question looks like, so this was for Kevin. When showing burner temp, is this the flame temperature or something else?
So I think, the team was testing two different temperatures. I think the one that we were showing was the temperature of the burner surface, not the flame itself. But I believe that was a temperature that we were monitoring. Unfortunately, I just don't have all those data results to display today.
No worries, thank you. So this is a question for everyone. When you do your testing and you're reporting 5, 10, 15%, do you start at 0% hydrogen and then increase it with the unit still lit, or do you restart it each time with the increase in hydrogen?
So maybe I can start with answering this question. Maybe Paul can follow up later. So for our testing at UC Irvine, actually we did both. And this is a very good question because we see different hydrogen blending limit for different appliances at different percentages. So for ignition, because it's the unsteady process, we see the hydrogen ignition flashback very early. For example, 20% flashback at for the cooktop burner. But later, so we want to see the the general influence of hydrogen addition on appliances. So we also did ignition with pure natural gas and then increase the hydrogen very slowly. So we could inject around 75% hydrogen into the cooktop burner without having flashback if we ignite with natural gas. So that's our observation here.
Great, thank you so much, Anne. And I know we might have more responses to the question, which we can take in the Zoom. So I know there's also a couple more questions that we didn't get to. So please move with us over to that Zoom session. And thank you again to our presenters, as well as to everyone who attended the session.